Welcome to part 2 of the notes on speed, velocity, and acceleration, and this section is going to focus on velocity. What is velocity? Well, if you don't know what speed is, you need to go back and look at the first video on the first section of notes, because velocity is basically speed, but it includes another component, and that is the direction. So it's speed plus direction. So some examples would be, say you're going 22 meters per second. That would be a speed. A velocity would just be adding a direction to that. So for example, east. That's an example of velocity. Or 14 meters per second south. Again, that's a velocity. It includes both the speed, which is the magnitude, and the direction. And turns out you can show velocity using vectors. And a vector is just simply an arrow that is usually showing both the direction and the relative speed. So for example, this vector, we might label it 2 meters per second east. And if I drew a bigger vector, we might label that one 4 meters per second east. So the size of the arrow shows you the relative speed, and then obviously the direction of the arrow shows you the direction. We can combine velocities of two objects because velocity is always relative to some other object. Actually, speed is also. So whenever we say you're going 60 miles an hour down the road, you're always comparing your speed to another object. Usually we mean the road, even though we don't say it. We don't say, I'm going 60 miles an hour compared to the road, but it's already understood. If you're, for example, on a bus, and the bus is going 22 meters per second east, and a person on the bus gets up and starts walking on the bus, but the person is walking at only, and the blue arrow represents the person, notice I drew it smaller than the first, is walking at 3 meters per second east. Well, that velocity is being compared to the bus, not the ground. So the first velocity, this velocity, is the bus's velocity compared to the ground. This velocity is the person's velocity compared to the bus. Well, if there was a cop, for example, out on the sidewalk, and he took a radar gun and he radared the bus, he would get a speed of 22 meters per second east. And let's just say the speed limit's 22 just for the sake of this. But if he accidentally radared the person, he would not get a speed of 22. He'd get a speed of actually 25 meters per second east. So when vectors are both going the same direction, we combine them and add them together. And the actual speed of the person walking forward on the bus is actually 25 meters per second east. And if the speed limit was 22 and that cop happened to accidentally radar the person, in theory the bus could get a ticket if the cop didn't realize he had radared the wrong object. So point of this is that when vectors are going the same direction, you add to get their combined velocity. This is called a combined velocity or a resultant velocity. And the other main point is that speeds and velocities are always being compared to some other object. This being compared to the bus, and the bus in this case being compared to the ground. Well, what happens if he goes the opposite direction? I'm going to pause it and draw a bus. Okay, I went ahead and drew the picture so you didn't have to watch that happen. Let's say we still have a bus here, and the bus is going 22 meters per second east. This time the person gets up and walks the opposite direction. So this time he's going this direction on the bus, but the bus is going this direction. Well, again, the bus's speed is being compared to the ground, and his speed is being compared to the bus or to a person sitting on the bus. So he's actually walking 2 meters per second in this direction. Well, what is his combined or resultant velocity? And in this case, we have vectors going opposite direction. And whenever you have vectors going in opposite direction, you just simply subtract. So you take 22 minus 2, and you would end up with a velocity of 20 meters per second. And you would always take the bigger direction. So the direction is east. So this person is actually, if he or she was being radared by a cop that was sitting on the sidewalk down here, the speed the cop would actually detect would be 20 meters per second east. And the thing I neglected to say on the previous slide is you can actually draw also the resultant vector. I'm going to draw it a little smaller than this one because this one is going 22, this one's only going 20. So that would be the resultant vector, a little smaller than that, pointing in the direction east. Well, so far so good with that. Turns out, though, of course, things don't always go in the same direction or exactly opposite. What happens when something's going 90 degrees? And this says bus example, but bus doesn't actually work for this. Could be an airplane, could be a river. The lab you did used a river as an example. And basically, if an object's going this direction, I guess we can say it's a boat, could be an airplane, and it has a velocity of 4 meters per second. And that would be compared to the water that the boat is in. But the water itself is moving this direction at a 90-degree angle to the boat. And we'll just say that this has a velocity of 3 meters per second. Well, what's the boat speed if you're a person out here on the riverbank? If you happen to have a radar gun, well, let me back up. Let's say you had a little thing in the boat here that could tell you the speed of the boat compared to the water. That's what you would get. Then you know the water is moving this direction in the river. Well, what if I'm a person out here with a radar gun and I radar the boat? Well, turns out you're not going to get either of those two numbers on your radar gun. You're going to get something different because the water is moving and the boat is also moving. You would get a velocity of a little bit bigger than 4, just using common sense. But you can actually figure out the exact velocity, and it's not just simply adding or subtracting. We can borrow a little math here, and if we just make a triangle out of this, we can basically set up the equation a squared plus b squared equals c squared. And using this equation, we can actually figure out if these were distances in a triangle, what the distance would be, but these are actually speeds, but it will still work for us. If we know this speed and this speed, we can figure out the resultant speed, which is represented by c here. So I did do this as this exact example in the lab video. So if you already saw that, you can probably fast forward through this if you already get that. So a squared would just simply, we can pick this to be a and we'll pick the 4 to be b, and then we can solve it. So we would just put 3 squared plus 4 squared is equal to c squared. We'd square that and get 9 plus 16 is equal to c squared. And we need to get c by itself. Right now it's being squared. And the way we do that, of course, well, let me first combine these units. This would be 25 is equal to c squared. And then we'd have to take the square root of both sides. So we'd take the square root of this side, square root of that side. That gets rid of the squares here, and we get 5 is equal to c. So the actual velocity of the boat, if this person radared the boat, he would actually get a 5 meters per second on his radar gun. This math might be a little beyond where a lot of students are at in their current math classes. So I just would expect you to know, if you don't understand the math part, that because you have two velocities, you have to combine them. And in fact, it would make sense that the actual velocity is a little bigger than 4. And it turns out it would actually be 5. Well, and that pretty much concludes the notes on velocity.